Welcome to The Explainer. Today, we're diving into a genuinely mind-bending physics paper by Kai Huang. This one completely challenges our most basic understanding of space-time. We're going to explore a framework that totally rethinks the quantum level and honestly questions the very nature of what keeps your feet planted firmly on the ground right now. So what if gravity is actually not a fundamental force? I know, it sounds like absolute scientific heresy, right? Since we were kids dropping toys on the floor, we've just accepted gravity as this fundamental pillar of nature. But the material we're unpacking today suggests a massive paradigm shift. It proposes that gravity might merely be an emergent illusion, like just a macroscopic side effect of something much, much deeper happening down at the level of quantum information. To wrap our heads around this, here's our roadmap. First, we'll look at Einstein's unanswered question. Second, a universe of qubits. Third, gravity as information stiffness. Fourth, three radical predictions. And finally, we'll hit the illusion of gravity. All right, let's jump straight into Section 1, Einstein's unanswered question, or the flaw in general relativity. Think about the incredible contrast between Einstein's massive triumph and a lingering, unsolved mystery that still haunts physics today. On one hand, we've got the solved part. Back in 1915, Einstein gave us general relativity, brilliantly describing gravity as the curvature of space-time. It's an absolutely elegant geometric intuition. But then we have this unsolved bare parameter problem. Where does Newton's gravitational constant, big G, actually come from? In our standard models, G is literally just a manual external input. We measure it experimentally, and then we just plug it into the equations. No deeper theory actually derives its exact magnitude from first principles. It's kind of just a blank spot in the foundational code of physics. Which brings us to Section 2, a universe of qubits, and the three axioms of HISGR. To solve this mystery, the author proposes a really radical new axiomatic lens, basically building straight from information theory. First, imagine the universe itself is pixelated into discrete qubits. The pure state space of a single qubit, which you can picture geometrically as a Bloch sphere, yields a maximum information entropy. Second, the absolute minimal unit of information in this virtual space maps perfectly onto exactly one Planck area. And third, because of that, there's a hard limit to how much information can be packed into a space. The maximum entropy density is 1/4 times the Planck length squared. Essentially, space is like a literal hard drive, and unlike your smartphone, it has a strict universal data limit that it absolutely cannot exceed. Now, the absolutely crucial point here is this specific fraction, 1/4. In the paper, this isn't just some random number. It's practically a mysterious code inscribed on space-time itself. This coefficient of 1/4 acts as a universal conversion factor. It translates between the abstract geometry of quantum information and the physical area of a holographic screen. It's the bridge connecting abstract math right to the physical reality we actually observe. Let's move on to Section 3, gravity as information stiffness. This is all about renormalizing G. This brings us to the core of the entire theory. Holographic Information Stiffness, or HIS for short. Try to think of space not as a totally empty vacuum, but as a super tight elastic trampoline. It desperately wants to maintain its uniform maximum information limit. So when you introduce matter, like a whole planet or a star, it adds a ton of information that perturbs this delicate system. Holographic information stiffness is the macroscopic elastic resistance of that virtual space, trying to push back and maintain its limit. And here's the wild part. By using the laws of thermodynamics and geometric identities, the author rigorously derives Einstein's equations without ever assuming gravity exists as a force beforehand. Gravity is literally just the elastic pushback of this underlying information medium. And the math here is exactly where that bare parameter problem finally gets solved. According to linear response theory, big G is actually a renormalized local quantity. In a total, pure vacuum, the gravitational constant is just the bare scale parameter, G0. But the moment you have the presence of matter, G actually changes. It gets multiplied by a specific factor based on the entropy density gradient of that local matter. So the big takeaway here is totally mind-blowing. The gravitational constant is not a universal constant at all. It subtly shifts based on how densely matter's information is packed in any specific location. All right, let's get into Section 4, 3 radical predictions, because we definitely need to test the theory. The HISGR framework elegantly solves three distinct observational and theoretical problems in physics. We're going to break down dark energy scaling, equivalence principle violations, and the black hole information island formula. First up, dark energy. For decades, the infinitesimally tiny value of the cosmological constant, the thing driving the expansion of the universe, has been seen as this weird fine-tuning coincidence. But under this framework, it's totally natural. Because our observable universe has a finite size, bounded by the cosmic horizon, there is a finite information capacity. Dark energy is simply a boundary effect. It's a natural entropy deficit that scales directly with the radius of the Hubble horizon. So it's not a mysterious coincidence at all. It's quite literally just the thermodynamics of a finite hard drive. Prediction 2 challenges another absolute sacred cow of physics, the equivalence principle, which basically says that gravitational and inertial mass are the exact same thing. But remember how we just learned that G shifts locally depending on matter density? This means extreme objects with massive many-body quantum entanglement, say a 1.4 solar mass neutron star, might actually experience a tiny shift in how gravity affects them. The formula provided strictly links that equivalence violation directly to the entropy gradient of that dense matter. It gives physicists a highly precise mathematical target to go out and compute. And the best part is, we can actually test this. Right now, the microscope satellite has set an upper limit on equivalence principle violations at 10 to the negative 15. The predicted signal of this information stiffness framework falls right around that exact frontier. Upcoming next-generation space experiments, like STEP, Tiankin, and ION, we're targeting sensitivities all the way up to 10 to the negative 18. That means in the very near future, we'll have the exact technological capability to directly probe and either confirm or completely constrain this matter-dependent gravitational stiffness. The third prediction resolves a massive headache in quantum mechanics, the Hawking black hole information paradox. Hawking realized that black holes evaporate, which seemingly destroys the quantum information inside them, breaking a huge rule of physics. Modern physics uses something called the island formula to save that information, which features a very specific area term. Well, this framework's axiom that the maximum entropy density is 1/4 of the Planck area provides the exact geometric unified origin required for that formula to actually work. It elegantly ties black hole thermodynamics right back to the fundamental limits of information space. Which brings us to our final part, Section 5, the illusion of gravity and redefining the physical world. I really want you to absorb this quote from the author, Kai Huang. Gravity is neither a fundamental interaction nor an intrinsic property of geometry, but rather a macroscopic elastic stiffness response of the virtual space. That is just a massive conclusion. The curvature of space-time that Einstein taught us to visualize is merely the macroscopic projection of this underlying quantum information stiffness. Gravity isn't pulling you down. The virtual space is elastically pushing back to protect its own information limits. Which leaves us with this final thought. Take a second and look at the chair you're sitting in right now. You feel gravity anchoring you to it, but if that anchor is really just an elastic response of pixelated quantum information fighting to maintain an entropy limit, what else about our physical reality is merely an illusion? Thank you for joining me on The Explainer. Keep questioning everything.